Okay, now we come to question 17. Question 17 says if the maximum intensity wavelength radiated by a star is 425 nanometers, what is the temperature of the star? And all of these temperatures are given in Kelvin. 6082 Kelvin, 7059, 4580, 5644. This topic has to do with the radiation spectrum of an object. Okay, this was studied in the 1800s, and finally Planck used this concept of the quanta to explain the equations behind this. It was discovered that objects, depending on their temperature, have a radiation spectrums looking similar to this. This graph is the plot of intensity of radiation versus their wavelength. Okay. All objects basically radiate energy, different wavelengths of the electromagnetic spectrum. So even I as a person am radiating based on my temperature, the body of my temperature, I am radiating. It happens that objects at room temperature radiate in the infrared mainly. So you can't really see it with the visible eye, but if you had infrared glasses, you will be able to see the radiation given off by the human body, right? So, and this is known here as the peak wavelength, lambda peak. That means depending on the temperature of an object, there's a wavelength at which their intensity peaks. Okay, so let's say there's another object. So let's just say, for the sake of argument, that this is a temperature 30 Celsius. Okay, that's going to be around what? 273 plus 30, that gives you 303 Kelvin. Okay. Now let's say there's an object that is much hotter. Okay. What happens to its radiation spectrum? Okay. What tends to happen is that their peak wavelength starts decreasing. It goes in this direction. Okay. So lambda peak. Okay. And not only that, but the intensity of the radiation also rises. Why? Because they are hotter. So I'm assuming this object is something like, it could be anything, let's say 1000 Celsius. Okay. Which is equal to what? 1273 Kelvin. And then if I keep doing this graph, right, I'm going to get, the progression is going to keep getting bigger. So the peak intensity is going to rise, okay, and it will be shifting to the left, right, towards shorter and shorter wavelength. Remember what we talked about before, the velocity of an electromagnetic wave, which is the speed of light, is equal to its wavelength times its frequency. When the peak wavelength is decreasing, what does that mean? That means the radiation that the object is emitting is becoming higher frequency, right? When the wavelength is going down, the frequency is rising, and the energy of a wave is proportional to its frequency, right? So when the frequency is rising, the energy is rising. So here's what's happening. As the object is getting hotter and hotter and hotter, it's emitting in the short wavelength spectrum, which corresponds to high frequency, high energy spectrum. So that only makes sense, right? So when an object is put in an oven, such as, let's say, an iron rod, and you heat up the iron rod, what is the first visible color that it will radiate in? It will radiate in red, right? First, when the iron rod is outside of the oven, it's radiating infrared. Then you put it in the oven, you heat it up, you see red glow, right? Then you heat it up some more, what should happen? The peak wavelength should go down. Then it should look eventually green. Then it should eventually look yellow, green, blue, indigo, violet through the Roy G. Biv, right? And then after a while, if you get it hot enough, it could actually radiate in the ultraviolet with a high intense radiation, right? And this is very useful for our understanding of the spectral types of stars and their temperature, okay? So the person who put this behavior in equation form, this lambda peak into equation form, is known as Wien. His last name is Wien, W-I-E-N, and in German we pronounce the W as a V, okay? And his equation is, we call this Wien's law, and we say lambda peak is equal to 3 million over the temperature as measured in Kelvin. This gives the answer in nanometers. Nanometers, and this has to be in Kelvin. Okay? So he was the one who gave this behavior of the wavelength of the peak based on its temperature. Okay? So if we can put this in now, here's 425 nanometers. I don't have to do anything with that. I can keep it in nanometers because this equation is already expressed in nanometer. And that's equal to 3 times 10 to the 6th over t, which is same as 3 million. And then t will equal what? 3 times 10 to the 6th divided by 425. So 3 times 10 to the power 6 divided by 425 gives you 7058.8 Kelvin, okay? Which actually is this one, B, 7059, right, Kelvin. That happens to be a star that is hotter than our sun. Our sun is 5800 Kelvin, which is cooler than that. So what would its peak wavelength be? This time we can divide 3 million by 5800. 3 times 10 to the 6 divided by 5800. And we would get 517.2 nanometers. That happens to fall in the green range, green-orange range. Okay, so 517 nanometers, whereas this one was 425 nanometers, right? So since our sun is colder, 5800, versus 7058, since our sun is colder, it is radiating in a longer wavelength. A longer wavelength means smaller frequency, which means smaller energy, right? So if there is a star that is even colder and colder, typically stars can get as cold as, let's say, 2500 Kelvin. The temperature is 2500 Kelvin. What wavelength will they predominantly radiate in? Well, they're going to be in the long wavelength region, right? So if you do lambda 3 times 10 to the 6th over 2500, 3 times 10 to the power 6 divided by 2500, that's going to be 1200 nanometer. So that kind of a star will predominantly radiate infrared. 700 nanometers is the edge of the red, 800, 900, 1000, that's basically going into infrared. What will that star look like to our eyes? It will look red, maybe deep red, like brown looking. So depending on its temperature, we can either call it a red dwarf star. If it's even cooler, we can call it a brown dwarf star, because it will be so dark and dim looking, it will have a brown tint to it, and we call those stars brown dwarf stars, and it happens to be actually not a true star. It's a star basically that is a failed star. Okay, it's not hot enough to be a true main sequence star. Okay, so you can see here that cooler objects radiate in a longer wavelength region. Okay, so you can now see how to use Wien's law and how Wien's law relates the wavelength of the radiation to the temperature of the object. Okay, thank you very much.